So we actually did a little bit of overflow work. And so we had timer 0 and timer 1 overflow circuits. And these overflow circuits have the ability to interrupt, and we can do all kinds of work with that. So next week, we're going to be working on a little project where we have the ability to actually use the interrupt to trigger an event, right? So this week, we're actually messing up a little bit with the analog to digital converter. That's going to be your laboratory activity. And so in that particular project, we have a bunch of push buttons, and then we have a single A to D connected to that series of push buttons, and then your software is supposed to connect to that, and then when a person presses a button, you should be able to tell me which button was the one that was pressed. Right, so that's what we're going to be doing today. Okay, so what we're going to be working today is called the capture circuitry, or the capture circuit. And this circuit comes from a capture and compare modules. And for the 18F4520, there is 2 of them. They're called the CCP1 and the CCP2 modules. And this capture module is pretty much nothing more than an external interrupt. And we actually studied external interrupt way back for exam number 1, I believe, where we were doing your external interrupts. Those were the circuits that you could find through this pound INT EXT, pound INT EXT1, and then pound INT EXT2. Those guys were located on port B, right? And they had the ability to look at an external event. These external events are electrical events. So these electrical events are either rising edges or falling edges at the specific input of that circuit, right? So a capture circuit is exactly an external interruptible circuit. They're exactly the same. What's the difference? The difference is that the capture circuit gives you the ability to timestamp that event, okay? So we have the event of having an electrical rising or a falling edge at the input of the CCP circuit, and the output is going to be timestamped. I know when in time that actually happened. And this is going to give me now the ability to determine the frequency or the period of those events being presented to the microcontroller. Does that make sense? All right. This, what you see in here, is what the data schematic or the data sheet explains to this CCP circuit to be. It's kind of like this very complicated mesh of a CCP point. So when you actually read this, there is 2 circuits in here. The upper part, this is your CCP1 circuit. And the lower part, this is your CCP2 circuit. They're actually fairly simple devices. So the first thing to remember is this. The CCP1 module is actually physically interfaced to pin C2, right? So that's the first thing to learn. So the capture and compare 1 module interfaces through pin C2. This is not multiplexable. You can't change this. It is just physically connected to that pin, and there is nothing we can do to it, at least in this micro. The CCP2 module is physically connected to pin C1, and you cannot multiplex it, right? You cannot change that connection. So if you really think about it, this capture module is actually not only a capture. This little box that you're seeing here is your edge detection device. It's the ability to see that rising or that falling edge, depending on the choice of the user. But there is something else. There is a prescaler attached to it. So for the first time ever, you're watching a prescaler in something other than a timer. So from the outside world, you can actually send a signal inside of this CCP1. So one way to think about it is like this. So on pin C2, I can send, let's say that I send a square wave. And this is going to go through a prescaling circuit. If you notice, this prescaling circuit can only be a divide by 1, a divide by 4, or a divide by 16. all right? So you can configure it to be a divide by 1, divide by 4, or a divide by 16. So what's going to happen is that after you have that divider, here's where you come to the edge detector. This guy is an externally interruptible circuit. The same circuit that you've been messing with in the first couple of weeks. You send me a signal, the microprocessor will interrupt and it will do some work, okay? So, what we are talking about is the ability to tell this device when in time this event happened. So I'm going to put here a question mark because we want to know when that edge actually showed up. So what's going to happen is that after the edge gets detected, an interrupt gets driven. And that interrupt is CCP1. Okay? So let me show you what that means. So that's pin C1. And here's where you find them in the circuit. CCP1 is located in C2. CCP2 is located in C1.
Who decided that?
How was that?
Who decided 2 was on 1 and 1 was on 2?
I think that there was an engineer that was pretty high on something one day, and he decided, you know what, I'm going to call CCP1 C2 and CCP2 C1. That's a really good question, and I think that as the more microprocessors you get to know, the more you realize that sometimes there are some decisions that make you scratch your head. So I don't know. That's a very good question that I can't answer. And so what's going to happen is that after I send my event, whatever that event is, the device will detect it and an interrupt gets driven. Now, the pound int underscore CCP1 is the interrupt that our compiler understands as the triggering event. So this guy will trigger this guy. If properly configured, of course. All right? Now the question is, what is that interrupt doing? Right? In the previous circuit, you press a button, the machine goes, I saw that. And now you decide what to do. In this event, it's a little bit different. You press a button, an edge gets detected, the microprocessor is going to interrupt, but it's going to now save the moment in time that this event was detected. Okay? So how does the machine does that? Well, you have two choices. You can either configure your system to work with timer 1. We already work with timer 1. Or you can use the system setup for timer 3. One or the other. In the 18F4520, the capture and compare module by default is going to choose timer 1 for you. So if you use CCP1, if you're going to be using CCP1, then timer 1 is my default timer. All right? So that means that if I do nothing, the machine will actually feed or grab the time, the moment in time that the event happened out of timer 1, and is going to save it into this little register called CCPR. Now, when you see these two registers back to back, it means that there is 2 registers, 8 bits each, and together they make one 16-bit number. Does that make sense? So time is going by, you press a button, the machine sees the effect, and then boom, it's going to store the amount of time or the moment in time that that happened into that register. So here is my timer 1 running all the time, and then you're getting here the time of the signal event detected, saved in CCPR1. All right, so that makes sense? Okay, so here's the deal. It means the following. Every time one of these edges is detected by this filter, CCPR1 is going to contain the moment in time that that happened. However, when the next signal comes in at t times equal some other time, right? Let's call it 1. When that happens, the data stored in CCPR1 is going to be lost, and a new piece of data is going to go in its place. So it is your responsibility that every time the microprocessor interrupts, you have to process the time first. If you don't process it, you'll lose it when the next event comes in. Does that make sense? You see the idea. This is nothing more than an electrical camera. right? We're going to take time snaps of an electrical event. Any questions so far? Doing good? All right, these are the registers that we're going to start studying because they are all related to this game, right? Notice that this guy depends on timer 1 to do its work. So what this means is that we're going to have several registers to play with. The controlling registers are going to be CCP1 con and T1 con, right? So this guy, the CCP1 con, this is the register that controls the capture and compare. So this controls the capture circuit. The T1 con, this guy controls the timer unit. See that? So these are the two important registers. Now, PIE and INTCON are necessary for our interrupts. So then you're going to have the interrupt driven, that's going to be INTCON. This is going to handle the global and the peripheral. And then you have PIE1. This guy is going to handle the capture interrupt. Right? So we have the capture interrupt. All right. So here's the deal. All right. The first thing we're going to have to do is that we have to start modifying our library, right? Just remember that every time you have a brand new circuit, we have to add the hookup so that we can gain access to all our registers. So my repository, the first thing I'm going to do is that I need access to CCPR because that's the place where my timing information is going to lay. So the first thing you do is that you have to create a 16-bit pointer for that particular register. So I'm going to call it int16, and I'm going to go star CCPR1. There's two registers in there, and you always choose the address to the low register, right? Always choose the address to the low register. So I'm going to just put CCPR1 to FBE. So this is FBE. So in memory, you have two boxes. One is called CCPR1 low. The other one is called CCPR1 high. This guy is FBE, and this guy is FBF. Okay? And so what we're doing is that we're creating a register that does not have any high versus low identification, and I'm pointing it to the lowest register. And that gives me the ability to wrap around the data, and I don't have to actually do any kind of data manipulation to obtain the data from it. Does that make sense? See it in here? There is the low at FBE, there is the high at FBF. And so you create a 16-bit pointer, and then you point it to the low element, and then that gives you the wraparound ability, right? No need to manipulate any kind of data manipulation. So that's the first thing we need to do. The second thing we need to do, we have to go to our CCP control register. This is on chapter 15. So the capture and compare module is on chapter 15. Okay? So this capture and compare module in chapter 15 is going to give us the following arrangement. You have 4 bits that together decide the behavior of the CCP circuitry. This circuit can work in 3 different modes. It can work in capture, it can work in compare, and it can work in pulse width modulated form. So there is 3 ways that you can use this circuit. It's a very nice circuit. And so these 4 bits are creating one unit. So this is my int CCPX-MX4. By the way, I saw this in exam number 1. I still, to this day, do not get perfect scores when it comes to the creation of these structures to gain access to the circuit, which means that for exam 2, I'm going to do it all over again. We're just going to do this one more time. All right, so make sure you practice this. It will be in the test. All right? So to raise the stakes, to make it even more fun, I'm going to make sure that that particular problem, there will be no partial credit. Learn how to do it, right? There's nothing better than give points to make somebody do something, right? Is that how it works? No, maybe not. So we're going to be adding this kind of stuff to the test again. And we're going to make sure that this time, make a little note in there, there will be no partial credit for this problem. So watch it, okay? Look, we're going to have our int. This is my data type. Int, my circuit, how many bits? The totality should give me 8. So you got 4 circuits, 2 circuits, 2 circuits, right? Any question on that? How is that done? So you're going to add this line, and then you're going to add that to your library. So the library has to include this part. Now, a couple of things that are important. In this particular case, the CCP1 circuit and the CCP2 circuit are actual identical twin circuits. There is no difference between them other than the location they're put in inside of the die. So that means that I'm going to create a structure that could be used for both. So look how I called it. I went struct, and then I go CCPX, right? So I went CCPX con. So the type is going to be used for multiples, and then we go int, and then we have the CCPX MX, 4 bits. And then the next 2 bits we're not going to talk about until we start messing around with pulse width modulation. So we got that. That is our just a little structure declaration. So we know what kind of structure we're going to have. And watch what happens next. We come here and we go struct. And we go underscore CCPX con. And then we go star CCP1. So I'm just going to hold your attention to this pretty quickly here. Just watch this. This is, for the first time, the data type is not matching the actual name of my pointer. See that? And the reason for that is that there is a CCP2 in this circuit. And you could do this. You could do struct CCPX con star CCP2 con, and then find the address for it and put it in there. So you can have the same structure type for the 2 circuits because these 2 circuits are actually equal identities of each other. Does that make sense? And so that's the part that I want you to just make sure that you keep in mind, okay? So add this to your library. So we can get the capture and compare circuit to work. All right, so that's our setup. So we got the ability to add a 16-bit pointer for the place where I'm going to get the time of all these events, and then I'm going to have another circuit that is going to give me the ability to gain access to my controlling pins. T1 con we did last week. And PIE we also did last week. So we don't need that. So we got those already. One of the advantages of having a library, you do it once, you know it works, you don't have to add it again. So we're not going to be doing those. Now, this is important because I want to call you the attention to register 15.1. So when you go to chapter 15 of your control register, here is the explanation of the 4 alternatives that you have to make your device a capture module. Okay, so here's how the instruction works. So if I was supposed to, if I want to make my circuit, my CCP circuit, a capture mode every falling edge, I have to put the binary 4 in the first 4 bits. But because I have a structure, it will look like this. It will look CCP1 con arrow CCPX MX equals, and then you put that number. You could do it in decimal format like that, right? I know there's 4 bits, and because there are 4 bits, you could do this in hex too. So instead of a 4, you could do hex 4 to explicitly force a 4-bit number into it, right? So you could do one or the other. And this will be every falling. This will be every falling edge. Now, if you really think about applications where you're trying to figure out what is the speed of a specific motor, or you want to know what is the acceleration of a device, or if you want to find some sort of a rotational speed or any kind of speed, you want either every falling or every rising edge, right? Because you don't want to miss any of the edges coming into, so you can properly determine how fast something is happening. So we're going to be doing today one of these. We're going to just show you how a frequency counter is built. So, so this is every falling. So now you understand the idea, right? If you want every rising, that will be a 5. If you want to only detect every 4th input, you make it a 6. And if you want to see it only every 16th rising edge, you put a 7 in there. Does that make sense? Watch your data sheet, right? That's the most important part. If there is anything I want you to learn from this class, by the way, the reality is that most of us will never end up working for microprocessor in a microprocessor related field. I understand that really well. So I don't want you, number one, to feel pressure that I have to learn every single topic that is thrown at me. That's the first thing. Number two, what I really, really, really would like you to learn is the ability to read that data sheet. If there is anything I would like to see is that. Because if you have that ability, the next step of really learning how to mess around with microprocessors will come from it. You understand what I'm saying? So there's going to be a lot of problems down the road where I'm going to force you to just look at a data sheet and make a determination to answer that question based on the data sheet itself. Okay? So that's the idea behind it. Okay, so any questions on how to set the capture mode? There's only 4 options, and they're actually spelled right there in the middle of the swing. All right? That's all you need to get the capture module set up. All right. These are 2 examples that I want you to have in the slides. Nothing special. It's just the example that we just wrote. And here is the software in context. So I'm going to write this out in the board as well. So this is the software in context. So we got to talk about this a little bit. All right, so the stuff at the top is just a preamble. And then after that, you have your interrupt vector. And this is where we're going to be putting our interrupt routine. So inside of this little span is where you're going to put your application code. And these application codes, you have to remember, every time you have an interrupt, you have to make sure of 2 things. Number 1, do not trigger another interrupt from within a subroutine. That's 1. And number 2, make sure that your code is small and fast. I don't want to create in there a really complicated piece of code that will collide with the next call. And so there are all kinds of guidelines for every kind of field that you go into. There are guidelines that tells you how much time you can spend inside of an interrupt routine. And so for us right now, we want to make sure that we spend as little as possible doing any kind of work inside of the interrupt routine. That's what the main code is made for. So you do all the processing in main, The interrupt routine is supposed to be nimble and quick. All right, so that's something that we're just going to be working with today. And then after this comes your main code. And inside of your main code, there's going to be your wild one, or wild true. And then right here is your setup. And that setup is the good stuff. Okay? So, if you're going to choose CCP1, if you want to use CCP1, here is your setup. One, you're going to need a tri-state C on a hex 4. This is going to make C2 an input. Right? That's the first part. By the way, this circuit is a lot of fun. This is one of the funnest circuits in this microprocessor, period. You can do all kinds of really cool stuff with it. So this is what gives you the ability to actually do closed-loop control systems with micros. I mean, this is like, for anybody who likes control systems, this is it. This is like, get ready, because here where the fun begins. All right, we can actually do really cool applications with this. So we have in here, the next one is my CCP1 con. And I'm going to do this every falling edge. So this is CCPX MX. And then I'm going to put here a 4. So this is every falling. So that's every falling edge. The next 3 instructions are just interrupt driven. It's only for the interrupt. So the first one is PIE1, and then you go CCP1 con. That's a circuit inside of it, and we make it 1. So this is just an enable. That's the first one. And this other 2, you know them very well. And these 2 instructions are showing up for every interrupt, the global interrupt enable. And we have the peripheral. We have the PEIE, and this is also equal to 1. And now we have a proper setup. Notice how short this setup is. It's not as extensive as the setup we had to do for. It's not as extensive as the setup we had to do for the AGD. The AGD is kind of like, there's so many instructions needed to set it up properly. Now there's one thing missing in the slide, and it's timer 1. So I'm making the assumption that you know what really you want. So here's the deal. Timer 1, I told you that by default, CCP1 is fed by timer 1. Okay? So if you don't want to do anything other than turn the timer on, that's the only thing you need to do. So the only thing missing in that slide is this. I want to do T1 con, timer 1 on, and I want to make that guy equal to 1. I think it's TMR 1 on. And that's it. This is your setup for CCP1 on a default timer. See that? That's it. Now, every time somebody says to me, oh, Alberto, I would like to have an application that can figure out the speed of, that code will pop up in my brain. Just like that. Every time. Oh, I would like to have a machine that has the ability to figure out the speed of a car driving through a street. That's the code that is going to come out. Why? Because I'm going to figure out a circuit that every time a car goes by, is going to give me an electrical signal that will interrupt the circuit, and I will have a snapshot of the time that happened, giving me now the ability to figure out time. Right? If you want to know how fast a motor is moving on a printer, you're in a printer manufacturing job and you want to see how that motor is moving and the motor is encoded, then it means that I can actually take the output of that motor, put it inside of the circuit, and I can tell you how fast is that motor rotating. I can have that ability, right? So that's what we're trying to do. We're trying to just utilize this circuit to figure out any application that contains speed. All right? So we're going to give you today like one of the most basic applications out there. But it's going to blow your mind how you start. For the first time ever, we're going to start showing you how to think in circles. not linearly, but you gotta think in circles. So we'll show you that in just a little bit. So here's my application. Are you guys okay? We're all alive? I think we're ready for spring break. That's what it is. Because I woke up this morning and my wife goes like, you're in very good disposition this morning. And I go, absolutely, spring break is here. And she goes like, this is really horrible when you measure your years by spring break, summer, Christmas break. She goes like, this is really bad. You need to just find a different hobby. So anyway. And golf season is amongst us, so it's just about to get started. So been getting ready for golf season all winter long. So
But you don't want to go play golf.
I used to, but I'm getting older, so I can't play in the snow anymore. We used to have a group of friends that we have this really old green jacket, and every summer we compete, and then we make our own masters around the state. And so it's a really horrible jacket. It stinks. We found it one of those like really horrible places. And then you have to wear it for the rest of the year because you're the champ. And so I don't know if you want to win it or not. So anyway, okay. So here's the deal, guys. Here's what we're going to try to do. I'm going to take a signal generator, and a signal generator is going to pretty much behave the same way that any kind of edge generator will work. Like an LM555 will do the job. I'm just trying to create a signal that looks like up, down, up, down, up, down, just like an oscillator. Something that oscillates, right? Something that I can figure out how fast are these signals showing up. I'm going to put them into a micro. I'm going to calculate the frequency and the period of the signal that's coming in, and I'm going to spit out on the LCD panel the actual frequency of the signal that I'm seeing, right? So today I'm going to show you how to figure out how fast this device can respond, or how slow can I actually take that signal before my device stops working, right? So we're going to talk a little bit about how I think about this project and how I come up with a solution. Okay, first things first. So let's say that you have a whole bunch of waves coming in, and we're going to just look at the rising edges, just for the heck of the argument, okay? So you have a train coming in. Your job is to figure out how often are these signals coming at you. In other words, can you tell me the period of that signal through software and hardware means? The answer is yes, and we're going to show you how to do it. So first things first, how do you tell time? Okay, so if you have two events, I call this the starting time. I call that the stopping time. And it's obvious that what we're going to do is that to figure out how much time between these two have gone by, we take the stop time and we subtract the start time to get elapsed time. Right? Make sense? That's pretty cool. Very easy, fine and dandy. However, this only makes sense if this measurement happened within one cycle of time. What do I mean by one cycle of time? If you have a watch, and you take a look at your watch, right? And you take two samples of that watch, you can tell me the distance in time or how much time have gone by subtracting the stop versus the start, only if you did not go over the watch once. In other words, you never overflowed the watch. Because if you overflow the watch, you have to keep that in mind. So for example, if the first measurement is at 5 seconds, and the next measurement is at 4 seconds, you did not move minus 1 second time. See that? You actually went 59 seconds. But the only way you know that to be true is that you know that that clock overflows at 60. I go from 1 to 60, and then 1 to 60, and then 1 to 60, right? So the only reason why you know that you did not travel back in time is that you are taking into account overflows. Okay, so if I put time for a microprocessor is not given in seconds but in counts, right? Timer 1 we studied last week. Just take a look at a crystal, a pre-scaled version of the crystal, and it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just counts. That's all it does. So that means that your watch, the watch for this problem, starts at 0 and it ends up at 2 to the 16 minus 1, right? Of course. So I'm just going to put in 2 to the 16 so it doesn't take too much space. But you get the idea. I have 2 to the 16 counts in one clock full cycle. I'm going to call that one overflow. Does that make sense? Okay, so any measurement of start versus stop that falls within one stop is calculated that way. Right? Good. What happens though if what I'm trying to do gets interrupted by an overflow in between? Right? What happens next? If you take a look at that case, this is where you have your start, you have your stop, and 0 to 2 to the 16 falls somewhere in the middle. And the clock begins counting again, all the way to the end of the overflow. You see that? So, let's write this down. So you have case number 1. So here's your case number 1. This is my start. This is my stop. This is time t equals 0. And this is time t equal to 2 to the 16 minus 1. So that means that timer 1 overflow happens at that spot in time. Right? 2 circuits. You have 2 circuits working at the same time. Right? Timer 1 is just going tack, 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 completely independent of CCP. Okay? 2 circuits, capturing and comparing one end, the timer on the other. The timer is always running, always running. So that timer is on the run. And the capture circuit is working underneath. And so the first time this hits, this information is going to go to CCPR1. And when this guy hits, that information is going to go also to CCPR1. Okay? All right. So I'm going to call this start, and I'm going to call that stop. We're looking for elapsed time. So we're going for this delta t. And we calculate delta t to be equal to the time when stop occurred minus the time when the start occurred, because both events are happening within one overflow. You understand that, right? Okay, now, that's my equation. Keep that in mind. So I'm going to repeat this. Here's case B. You have up, down, up, go. This is my start time. And this is my stop time right here. Right? But here's what I'm going to do now. I'm going to make my time, this is your timer t, this is t equals 0. And right in here in the middle, I'm going to put here, this right here becomes 2 to the 16 minus 1. So this is going to be a T1 overflow, and I'm going to put another T1 overflow here. Okay? So this setup that you see right here, that's the setup that I'm showing you here. Right? So if you're going to find the elapsed time between these 2 green lines that you see on the slide, what we need is the following. I need this time as portion A, and then I need this piece. This is portion B. See that? So the way that you calculate this is as follows. I have to take 2 to the 16 minus my start time plus the stop time. You see that? So this is going to be my delta t is going to be equal to 2 to the 16 minus the start time plus the stop time. See the difference? This is my new formula. Am I making sense? So there's your formula. I'm going to put here, there is one overflow that occurred between the two events. So this is one overflow times 2 to the 16 minus the start plus the stop. That's what we have in there. See that? So let me extend this. Let's extend this behavior, okay? I'm going to repeat this problem now, and I'm going to put here 2 overflows. Here's the 2 overflow example. The 2 overflow example is not in the slides. I'm just going to put it in here on the board, and it's going to look like this. We're going to have low, high, low, high, low. Here's my start time. This is your stop time. Okay? You have times t equals 0. And so I'm going to put an overflow right here. So I'm going to go right at this spot, and I'm going to overflow it once. And then I'm going to go right here, and I'm going to overflow it again. And I'm going to go right here, and I'm going to overflow it again. Okay, so here's what we have. I'll let you jot this down a little bit there. Okay, here we go. Here's what I want. I need to take into account this, right, plus this, plus this. Right? There's 3 pieces to this. You agree with me? There's just 3 little chunks that I need to do. If I want to find the elapsed time from that spot to that spot, you need this little sliver, you need this guy in the middle, and you need that little sliver to get the overall time, right? So this guy, every time one of these overflows happen, your clock begins back at 0. So every time this overflow happens, my clock begins back at 0. So the only way that I can get this piece right here, to get that little piece, this is going to be 2 to the 16 minus the start. Right? So that's my one overflow. This part is just 2 to the 16. See that? And then this little sliver here, this part, is just t stop. So what do I get? If I put this stuff together, it's going to be 2 times 2 to the 16 minus t start plus t stop. What's the pattern? Number, exactly right. It's going to be number of overflows times 2 to the 16 minus the start plus the stop. Because if I make the number of overflows equal to 0, 0 times 2 to the 16 goes away, and I have stop minus start, which is that. If I make my value of overflows equal to 1, I'm going to have 1 times 2 to the 16 minus start plus stop, which is that. Right? So here's what I mean. It means that my formula is that. This is your formula. If you want to know how to calculate time, listen to what I'm going to say. If you want to know how to calculate time in a microprocessor that has an overflowing clock, that's the formula. The only thing you need to know is how many bits your timer has, and you need the ability to count overflows. But I have a circuit that can detect overflows. So what does this mean? It means the following. In order for you to tell me the speed of a system, I don't only need a capture and compare interrupt, I also need an overflow interrupt. Because I have to tell you how many interrupts since the last time I saw that event. So now I have two interruptible circuits working together to create one application. That's the story of microprocessors. You are integrating circuits together to create new applications. That's it. Not very complicated at all, right? So this formula is what's going to be inside of the capture and compare module. Every time one of these edges shows up, I will look at it, look at the past, calculate the amount of time in between, and that way I can tell you what's the frequency or the period of the signal that I'm seeing. Does that make sense? All right, here we go. One more thing. If you take two of these events back to back, right? Look at the first event. I'm going to put them here in red. So at time t equals 0, my first starting event occurs. At time t equals 1, the stop event occurs. But notice that when time t equals 2 event shows up, this 2 event is the stop of the previous event, but the start of the next. You see that? This is a cycle. Every time I capture a brand new piece of data, that piece of data that I just captured is the stopping for somebody, but the starting for the next. You see that? Now here's the trick. When you try to make these kind of circuits work, you have to think or program from the end. You cannot program from the beginning. If you do, your program is going to look out really funny. And your code is going to be very complex. You have to make the assumption that you are going to begin from the end, so that when you see me coding now, I'm going to make the assumption that when I capture, I'm capturing the stop. Here's why. If I capture the stop, I'm making the assumption that in the past, I also capture the start. So when the stop shows up, I am ready to make my calculation. See that? The problem is this. The first time your software goes through is going to give you out junk data. Why? Because there was no start to the first event. So when this guy shows up for the first time ever, there is no start. So this is the first start, but I'm going to assume that that's a stop. I'm going to make my calculation and then move to my next event. When that happens, that stop will now have a proper start, and I will be able to do my code. So what you're going to notice is that the software that I'm going to create for you now is a piece of software that begins thinking at the end. Right? That's the idea behind it. Because one cycle start is the other cycle stop. Right? So that's the idea. Now, look at it. Here's the code. So I know that my circuit, every time an external event at C2 is detected, the interrupt will trigger, right? When the interrupt triggers, the first thing I'm going to do is this. So I'm going to go here and call it T-stop. And I'm going to call CCPR1. See that? Within milliseconds or microseconds of this device triggering for the first time, I take the data from CCPR1 and I save it in a variable so I don't lose it. That is going to be my stopping spot. Notice that I did not call it start. This is my stopping point. I want to begin at the end of the circuit. The next thing I'm going to do is that I'm going to make the calculation of the equation that we wrote before. So I'm going to call that delta T, and that's going to be X. That's going to be the number of overflows times 2 to the 16 minus the start known as this T start, plus T stop, right? So this instruction is overflows times 2 to the 16, right? You could have written like 216 or something like that, but it's better to write it in hex, I guess. So this is just the instruction, the standard math. Once you have the standard math, this is where we get ready for the next cycle. So the only thing we're doing now is just cleaning up so that the next cycle in, we're ready to receive the stop of the stop of my cycle, but the start of the next, okay? So it goes like this. Now I'm gonna take my T start, and I'm gonna make it my previous stop. And then I'm gonna take the number of overflows and I'm gonna clear it out. And that is your frequency counter. 4 lines of code that can put food in your family's table for a long time. That's it, just 4 lines of code. This is taking care of those cycles that are showing up. So something comes up, I grab the time that it happened, I compare it to the past, and I cyclically do this over and over and over again. So that means that delta t, now listen to what I'm gonna say, because this is gonna come back to haunt you. Delta t contains the number of time counts between 2 events at C2. See that? Delta t contains the number of T1 counts between 2 events at pin C2. Right? So if you really think about it, at pin C2, you have something like this. This is event 1. This is event 2. In between these 2 events, timer 1 is ticking. Right? This is T1C. See that? So this is an interesting device. It's a very interesting device because this thing now, while the events are happening, this is happening at C2, and every time this event happens, I'll take a snapshot and I save it. And this continues ticking, tack, 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 tack. When that event happens, I take the sample, I do the math, and this variable, delta t, will contain how many of these T1Cs occurred between these 2 events. See that? That's what we have. So, mathematically speaking, I could calculate if delta t is equal to 3,520, what is the frequency of the signal at C2, assuming a free scalar equal to 1 and a frequency of oscillation of 20 megahertz. All right? Sorry, Paul. I got this. Get in there in your way. So if delta t, notice that I'm asking a question that has 2 constraints. Number 1, there are some physical quantities that determine how the timer is working. And 2, I'm actually making an illusion. I'm actually bringing forth a piece of software that you've seen before. So I'm saying, if this delta t turns out to have inside of it, somehow this calculated it, and inside of it I have 3,520. That's the number I find in there. If that's the number, tell me the frequency of the signal that actually made that. Right? That's what I want to know. So here's how you do it. First things first. I need to calculate T1C. This is going to be 4 times 1 divided by 20. And the reason I remember this is because we did that last week and I had to write it in the notes, so now I remember what it was. So this is 0.2 microseconds per T1 cycle. Every cycle. I'm talking about every count. You can call that a count, a T1 count, whatever you want to call it. Per cycle, per count, per... So how much time between every count, right? So now that I have that, delta T is 3,520 cycles. So if I want to know the period, so the period of the signal at C2 has to be equal to T1C times delta T. So it's going to be 0.2 microseconds per cycle times 3,520 cycles. This cancels that. And we're going to get I got 0.704 milliseconds, right? This is 0.704 milliseconds. That's this. See that? And then frequency is 1 over that. So the frequency at C2 is equal to 1 over the period at C2, which is equal to 1.42 kilohertz. See that? So this piece of software, the way that it was created, gives you the ability to calculate how much time have elapsed between 2 events. See that? Remember, this is an instantaneous measurement. This will not give you any idea about trends. You will not see any trends. From trending advice, you're going to have to go to the next class, and then they teach you how to actually take into account trends. For that, you use derivatives and integrals, and you figure out a way to actually add derivative and integral control inside of your software. And that is a whole nother story. It's a different ball of wax. There is like 6 different algorithms to calculate derivatives, and like about 7 different algorithms to calculate integral, and the battlegrounds are out there. And so there's all kinds of fanboys and fangirls that like one over the other, and the battleground will continue to the end. And so I don't think that that question will be answered anytime soon. But you see the idea, right? You see how this goes. And if you want to see how teachers think, right? It is not out of the question for me to say, if I drive a signal at 2.3 kilohertz at C2, what would be the value of delta T? See, working backwards, right? I mean, it's kind of like, if you're a teacher, you would do it too, right? It would be like, I give you the kilohertz, you find T. Once you find T, you figure T1, and then you can solve by that, right? I'll leave that to you. Leave it to your imagination. So Legend says the teachers love to give their work to work this problem backwards. But that's just a legend. All right, so let's add to this. This piece of code that you see in here is the one that we just put on the board. So that guy is just, nothing has changed, but look what we did in here. We added timer 1. This is an overflow circuit. This is the circuit from last week. Same circuit. The difference is that this interrupt is just going to count the number of overflows. So notice that when the event happens, when one event is detected at CCP, the number of overflows goes to 0. And the next time an overflow happens, this guy will say, oh, I saw 1 overflow, 2 overflows, 3 overflows. And so when the next event happens, I will have the overflows ready for my calculation. You see that? So you got 2 circuits working without actually having to schedule a handshake. See that? They're independent circuits working independently. See that? We're going to do this in class now so you can actually see it. Here is your main code. This is how the main code is going to work. I just need D1C, my LCD in it, the 2 pieces of code we just did in class right now. And then you just simply print out delta every so often. And then that will give you the frequency of the device. All right? So here's what we're going to do. We're going to actually write this down together in our software. Okay? So open up Proteus and Pixie. So we're gonna transfer to that. Okay? Here we go. So first things first, we're going to get started with our library.
That works better. That's good. You couldn't see it.
Yeah. Okay. So the first thing I'm going to do is I'm going to open the library. I'm going to make sure that we get this library. And I'm going to add the capture and compare stuff in here. So I'm going to go CCPX, related. So we're going to go struct, CCPX on, int, CCPX, MX, 4 bits, int, CCBX, 2 bits, unused 2 bits. Okay? DCXPX. All right, so that's one. So let me get I'm going to go structure CCBX con, and then we go CCP1 con is going to be FBD. And I'm going to put the other one too in here just to make sure that we have them both for later work. Down the road, we're going to have a project in which we're going to need both CCPs together at the same time. So I'm going to add it in here. So let me look for, I got to look for that. just looking for the address. So I opened the data sheet to look for that. So base 65, I will find. CCP2con is FBA. So I'm gonna put here text FBA. Right, so we have control of those two. And then the next piece that we're gonna need is a 16-bit pointer for the time. So CCPR1 is going to be equal to FBE. That's from the slides. And there it is. This is all the control we need for our capture and compare related registers. That's all we really need. If you remember T1con, we should have it already. So this is my timer 1 on that we need. So that's already been set up. And we also have a PIE that we did a while back when we were working with the analog to digital converter unit. So these are all in here already. This is, once again, reusability of code. When you actually make a library, all of a sudden you tend to realize that code reusability is very useful. It's something that we can rely on for years down the road. Okay, so that's all we need. Once you have this file open, by the way, this is something I saw last week quite a bit. If you try to compile this, the compiler is going to spaz out and say that I can't do it. A dynamic link library issue, it just gives you these weird errors. So if you go here and compile, it breaks out error file, like you can't do it, or file not found. You can't compile a header file. I guess that's what it goes both down to, okay? So don't compile your H file. So I'm going to close it, and we're going to create a new one. So we're going to go File, New. I'm going to create a brand new folder, and I'm going to call this Capture Module. And Capture CCP1 Test is what I'm going to call this. And I'm just going to simply type what we put in the classroom, okay? All right, I'm gonna take a look, make sure that this is finding it. It does. So if you notice, one of the reasons why we have this very strict structure for our folders is so that every week, as we're going in, it pretty much creates an automatic way of finding my files without having to sweat it too much. So it's kind of like a very good idea to make sure that all your files have a very strong structure to them. I think I don't think that in engineering school they ever taught us that. Like version control, make sure that your files are well documented, make sure that your files are placed in a structure that is easy to find, naming conventions. That stuff is usually forgotten in school. I understand why at the same time, but when we go to work and you're trying to manage a bunch of people doing code together, it becomes one of the most important topics in your day-to-day activities. It's just, where do you find things? How do you call them? Naming conventions. So keep your files neat, clean, in proper structures, and it makes your life easier. Okay, so anyway, first things first, I'm gonna start with my interrupts. I'm gonna put int timer 1. This guy is your overflow. So we're gonna go void int timer 1 ISR. And the only thing I want in here is just to count the overflows. So I'm gonna put here counting overflows. Okay, so that's that. The next part is where we're gonna make variables that are a little bit bigger. This is gonna become clear in a little bit why I'm trying to do 16 bits. I might actually go even larger, and then we'll explain to you how this happens. But this is going to be T start, T stop, and delta T. Okay. And then we go int CCP1, void int CCP1 ISR. So the first order of business is to get the stop. So this is CCPR1. And then we calculate delta T, which is x times hex 2 to the 16, like that, minus the start plus the stop. And then this is where my start gets refreshed. And my X gets cleared, and that's it. That's the frequency counter. Once you have this, it's just time to just set up your circuit. So I initialize the LCD panel. So I need my LCD panel, so I'm going to add it here at the top. I forgot. I'm so sorry. So I'm going to go back to my library. I'm going to pull the modified LCD.h. And then you can actually do your init in here. So this code is going to be online just a little bit, okay? So we got reprocessing commands. Then we have the actual timer setup. We got the frequency counter setup. And then now it's just the control stuff. So we go tris C hex 4. This is C to input. And then we go CCP1 on CCPX MX equals 4. This is every volume capture. Then we do PIE1, CCP1 IE equals 1. This is an interrupt enable. And then there is the standard stuff. This is the GIE. GIE equals 1. And the PEIE equals 1. Okay, so these are general interrupt stuff. So I'm going to do something here that is kind of like, this is something that I like to do myself because I like to keep chunks of code or blocks of code in logical units. Because this is a general interrupt, and for the first time we're going to have two interrupts working at the same time. I'm just going to separate this with a little bit of space so you can see what's happening. This is where I turn on my timer. T1 con TMR1 on equals 1. So this is timer 1 on. And the second thing I need to do is that I gotta find the overflow interrupt, right? Remember that? So we gotta find the overflow interrupt from last week. Now, if you were faced with this, the first thing you could do is just go to last week's code. So you go to T1 overflow and open the test code. It is in PIE1. See it there? So I just copy and bring it in. So I just copy and paste. So this is timer 1 overflow interrupt. And this is just the general interrupt, and that's it. So that's how the code is broken. It's broken in these 4 pieces. You see that it looks like a lot of code, but when you break it down to its most basic form, there is nothing really special about it. It's just a CCP setup, timer setup, interrupt setup, frequency counter code, just overflow counter code. That's it. So, all right. Okay, so once we're here, we can start our main program. So our main program is going to be a while 1. And then the only thing I want here is just to print LCD /f. If you want to see the period, So period is calculated. I'm going to put %f, and this is going to be T1C times T stop. Delta T. All right, so we got to calculate T1C, right? You can calculate it with a variable, or you can calculate it there on the spot. Okay, so you can make this 0.2 micro. I think it's 0.2 microseconds. So you can go 0.2 e to the -6. So you can do it that way, or you can create a variable for it. So if you want to change the prescaler for any reason, you can go and do it here, and then go 4 times PS divided by frequency of oscillation. So you can do this, e to the 6, and then I can make this one of them a float like that. And then you can go here and put T1C here. See that? That's just the calculation on the board. And then I'm going to put a little delay because my code is doing absolutely nothing, and I don't want the LCD panel to get absolutely blasted by the main code. So I'm just going to slow this down just for that. And that's it. There's a frequency counter. Well, you won't compile and then we fix stuff. Yeah, what do you know? Compile right back. I think this has happened just a few times in our history. I remember one day we were working on this project, and we were pretty much programming for several hours. I mean, this is nothing like you will recommend, but we're just going for like a couple of hours. And then somebody says, you know, guys, I think we should compile. You just press the button and boom, compile. We took it, dumped it into the micro, and somebody said, what are the odds that this will work right off the bat? And boom, it did. It was celebration time. Never happened again. It would never happen again. It's one of those things that you don't even know how it happened. We just got big time lucky. Okay, so here we go. So that's my code. All right, let's go to Proteus now. And I'm going to be opening the same software that we had, or the same hardware that we had last week. And then I'm going to rename it. So this is the circuit that we're going to be using. I just opened one that I already have, and I'm going to go File, Rename. So I'm going to save the project as, and then I'm going to go to my brand new capture module. And I'm going to call this capture module circuit, right? That's it. That's all we need. Because this guy is already working. Now, the only thing that we have to work on is our signal generator, because I know that on C2, that's my input. That's where CCP1 is located. The signal generator is actually found, there's this little button that looks like a sinusoid. And so I believe that in here, you can find your signal generator. Let me see. Actually, no, I think it's down here. This oscilloscope, logic analyzers, signal generator right there. So there's a signal generator right here on the instruments button. So I'm going to bring this up. The only thing you need is just to connect this to C2. So I'm going to use bidirectional ports. So I'm going to put one here. I'm going to put another one on C2 right there. And I'm going to call this SG, like signal generator. And they're connected. The only thing I want to do also is that it would be great to have some sort of a reference for the device. And so that's that. I have my reference in. And then we're going to load the software that we just created. All right, and then we got to make sure that we get this right. If you notice here on the right side, I want to make sure that you have this into square wave mode. And instead of bipolar, you want this unipolar. So this is unipolar square wave. And then I want to make sure that I got 5 volts. So this is 1 volt. So this is this times that. So this is a 1. So I'm going to go 5 volts in here. So that's my 5 volts. And so I'm just gonna crank this up a little bit. I'm about 1K. Let's see if it doesn't work, we'll verify what's going on. .1 unipolar. Good. Okay. Oh, the software is not working. All right, so we gotta troubleshoot it. So the first thing I'm gonna do is make sure that all my overflows are working. So I'm gonna stick. I'm gonna put a toggle on what am I not using here? C7. So I'm gonna stuck a toggle here on pin C7. And then I'm gonna stick a toggle here on pin C6. So my C7 is going, but my capture and compare is not. See that?
Do you have it on the right?
I don't know. Probably not.
Looks like you have it on C3.
Yeah, that could be it. Yep. There it is. All right. So that's the period, 1 millisecond. 1 kilohertz. It's about 1 kilohertz is about 1 millisecond. So there it is, 1 milli. So there. So I can take away my crude attempt at troubleshooting. All right, so that's that.
What's that thing called that you put in?
The what?
The signal generator.
Yeah, just a signal generator. The other thing we could do is just calculate the frequency. So if you want to calculate frequency, you just go to your code and put another print. So we could do something like right here. We could do /n. Let me just make this a little bit more compact. Go /n, and then I go frequency is %f, and so we take this and we calculate it as 1 over that. Right, done. And then you run this, and there it is. And so you can change the frequency a little bit. So this is 850 hertz, about 655 hertz. You okay? There you go. 690, 103, 1.09. Now this has its limits, of course. If we just go really low, eventually we're going to lose the ability to tell frequency. And if you go really fast, it also is going to lose its ability to tell frequency. Now, usually these are topics that we do not cover heavily in this class, but the ability to tell slow-moving signals is actually limited by memory, how much memory you have available, because you got to store a lot of ticks in between. And the ability to detect really fast-paced signals that are coming in is actually limited by the speed of the clock that is driving the micro and the speed of the clock that is actually capturing. So you got 2 clocks that you have to worry about. So usually it's about 4 clock cycles minimum that you need to get this to work. So yeah, and then, I mean, the next step in the evolution of your learning as time go by is to actually make sure that this is very accurate. So accuracy comes later. First, I just want to make sure that you know how to make something like this work. But you see that, right? You see how that's going? Now, here's the deal. Here's the deal. Notice that this piece of code was actually created to look at a signal generator, but I can actually now put in there anything I want. Look, what if I get a motor, let's say. So I'm gonna go here and I'm gonna go find myself a motor. So I'll go DC motor. Let me see if I find something useful here. The DC motor, here's an encoded motor. So let me pick this one. Motor encoded. And you take that encoded motor, I'm going to put it here, and I'm going to take power, I'm going to put it on one end. I'm going to put ground on the other end. And I'm going to take this generator. Cancel that. And I'm going to put it in one of these generator signals. I'm going to take my oscilloscope. I got an oscilloscope here, so I'm going to put this guy the same spot. I want you to see what's coming out of that. So while that motor is rotating, what these guys do, they take the shaft of the motor, and there's all kinds of different means by which we can do this. One of them is like a little sticker that goes actually on the shaft itself. And what it has is like, they have little like reflective surfaces that are created with a laser. And so you put a reader on it, and as the shaft is moving around, the laser is giving me shiny spots and dark spots. Sometimes they put 150, 160, 170 of those spots in the shaft. So every time the shaft goes around, I can actually see 161 pulses coming from the motor. If now I have the number of pulses coming out of the motor, and I also know that I have the ability to tell you how much time in between every reflective beat came through, I can now tell you what the revolutions per minute on that motor really is. See that? So if you want to know how fast a motor is running, you want to know the RPMs, that's how you do it. Right now, this motor, I just put 5 volts into it for the heck of it, and it's running right now at 140 hertz. So what that means is that whatever is coming in there, those little pulses are showing up at about 140 hertz. So there is right now about 7.118 milliseconds between Chinese spots coming out of that encoder. That's what that means. And so you can buy any kind of encoder. But the beauty behind it is that now I have a micro that costs under $5, that it gives me the ability to tell speed. So if I want to manipulate the speed of that motor for whatever reason, let's say that a motor is going too fast and I want to put an alarm, that's the code. See that? And so you begin with a simple signal generator, a capture module, an overflow module, put those two together, and boom, I can tell frequency. All right, so I'm going to put this online so you can have it, okay? So here we go. You can clear that. So let's go online. So I'm going to go to in-class code, and we're going to take capture. Come on, machine, you can do it. All right, here we go. Let's try to find that. So we're going to go micro spring 19. That's not what I want. Capture. Type. You want the C code. You want Furnace project. You want the library. right there. So you should have that. So your goal for today would be now to try to get that, to replicate that in your Proteus, so that now you have a piece of software that actually works and that you can trust down the road. So now for the next few labs, we're going to start cranking a little bit the difficulty of the exercises that we're doing. And so this week, you're doing the exercise of the 4 buttons on a single ATD line, right? So that's the exercise for this week. And then after that exercise is complete, next week, we're going to have a timer and a capture exercise, right? So we're going to have 2 of those. And then we're going to follow this next week. We're going to be doing 2 modules in 1. So we're going to be working with, because we have spring break, and after spring break, we're pretty much getting very close to the April. We're going to be 1 week away from April, pretty much. So during that week, I'm going to be covering compare mode, which is the premier way of creating interrupts in a microprocessor, much better than the overflow. But the reason why I showed the overflows is because it's used in the capture module. That's all we're doing with that. After we study the compare is a very simple circuit. It's a very simple idea. And so once we're done with the compare, we're going to do the easiest circuit to set up in the history of microcontrollers, which is the PWM circuit. So we're going to be doing those 2 circuits. After that is done, we're going to have our next test, and we're going to have a challenge. So that project is going to hit. It's going to take about 2.5 to maybe 3 weeks before you bring it back in. It's going to be a little bit harder project. It's going to force you to put a whole bunch of pieces together to make this work, okay? So just kind of like to give you a kind of like an overview of what's coming in the next few weeks. So try to finish the labs as much as you can. I'm going to be giving you some feedback. I added a new version. If you take a look at the lab at the bottom, I want to make sure that we avoid all kinds of misunderstandings. And so I added that reference at the bottom end. And the reason why I'm doing this is because this is this is common practice in software companies. If you're doing a piece of software and you're working with your lead engineer, there is something that we use a lot. And so we actually use repositories to keep track of what's happening with the pieces of software. But in order for us to really understand what's happening within a company, it is always extremely important to know who's helping who. I don't care where the code came from, right? What I want to make sure is that there are no misunderstandings in the process. And as you guys move on into a professional level, you have to give credit to whoever was the person who actually came up with the idea, right? I don't care, from my perspective, I don't care if you can solve the problem or not. What I want to see is your effort put on the paper so that I can help you get better, right? And so I just want to make sure that to avoid any kind of misunderstandings, if you have that code that came from help from person A, B, and C, just simply reference it. Put it in the reference. Hey, I was working with so-and-so, and this code was a together effort. Or, you know what, I was very confused about how to solve it, and I saw the solution from so-and-so, and that person helped me figure it out, and I figure it out that way. I understand how it works now because they helped me do it. And that's a valid reason to get your credit, all right? That's a totally valid reason. I want to make sure, however, that in the software world, when there are no references, the software world is brutal out there. They will come back at you, and people lose their jobs for stuff like this, right? So usually what happens is that you get assigned to a lead engineer. The lead engineer helps you. You create the code. You submit the code at the end of the week. Every software engineer has to submit his code at the end of the week. You submit it and you go, during this week I have been working with my lead engineer so-and-so. And do boom, that's it. You gave credit to the person that was helping you. And that's great. That's perfectly valid. It doesn't make you a less engineer. It actually makes you a better engineer. Because this way we understand where the knowledge is, all right? So I added that section to the labs. Make sure that every time you finish your lab, you just simply say, I'm just going to give credit to so-and-so for helping me with this piece of the code. Done. Moving on. Or if you work it on your own, you don't put anything on the references. You don't have to reference anybody. You don't have to put credit to me, right? It's like Albert Einstein's papers. Have you seen Albert Einstein's papers? Go to the references of his generalized relativity equation. References. None. It's like, you slide on. The first man in history that goes like references? None. Yes.
Didn't Emmy Noether develop those?
How was that?
Emmy Noether, he developed the field equation.
The field equations, yes, but the relativity equations, no. It was pure seminal research that he did. Yeah. No, they were not Maxwell's. Maxwell's have a lot to do with it. Maxwell actually work a lot with strong and weak forces of electromagnetics. He also have a lot of information about how the magnetic works in a general field. But the relativity equations, in particular, when he actually adds space-time as a movable unit, that was very seminal. That was his own. Very much a revolution. People hated him for many years because of that. And so it was very seminal. The one that is very difficult to read is the special case. And I've been reading that for years. The first time I was introduced to it was back in the 80s. And still to this day, I can tell you without a shred of a doubt, I don't fully understand it. So it's a beautiful paper, though. And so in his second paper, he actually had some references. The first one, he put none. So, all right, anyway, we're done. Make sure you get that done, okay?